in any case. It's in the kitchen. Thank you.
West.
Okay, lab assistant, one more thing. Mom, AKA lab teaching assistant.
Yeah.
Would you grab me my wallet?
What?
My wallet. I think this battery is dead. It's in here.
In your bag?
It's in my bag, Mom. Not that bag. The little bag. Do you see it? It's black. It might be underneath my bag. Mom, it may be underneath the computer bag. Look under pick up the computer bag. The computer, the brown one. Is it there? Oh, never mind. I'm just not gonna wear it. I'll look for it afterwards. If it's anywhere near that, it'll run down the battery. So.
And I
Don't worry
get
about
you
it.
another battery.
Yeah, go. Yeah, please. Hi, good morning.
Good morning.
For anyone who still can't access the lab manual without being on the 2-week thing, did you see my email? My email announcement? If you didn't see it, tell me. Somebody say something, because I got an email this morning about it. So if you didn't see it, let me know.
I saw the email. Yeah.
Does it work? Did you try it? Does it work?
I haven't had luck yet.
Okay. If it doesn't work, I'm going to ask you to send me a screenshot showing me what you get. You know, show me the thing saying it's declining you and it's not letting you do it.
Okay.
Because that's when I'm going to send back to the person over the books.
Hey, Professor, I was just looking for your email and I realized I tried to email you yesterday and it did not go through because I emailed it and I wrote RDU, not EDU. So it never went through you.
RDU.
Instead of .edu, like your email address, whatever, edu. I sent RDU.
Can you tell me what the email said now?
I was asking about missing assignments because I feel like I'm missing a bunch. I feel like I'm not navigating through this page correctly.
What?
Page. And then also I was not able to access the labs as well.
Okay, but can you get on McGraw-Hill Connect?
Let me try. McGraw-Hill, because I remember doing the deal.
All I see is MLB. Who am I talking to again?
Miranda Brandt.
Miranda, can you share your screen if I let you share your screen? Give me 1 second. I've got to get myself so that I'm set up to allow you to share your screen.
Okay.
I'll stop. Okay, so share it. So at the very bottom of your Zoom, one of the options is to share your screen.
Okay, so then I'm here.
Okay. So go to click on, actually do it a different way. Do it a different way. I don't know how you got here unless you, I don't know if you just put in
I
connect.
typed McGraw Hill.
All right, we'll do it this way. Go to Brightspace D2L. Now click on our class. Click down to quick week 996, that one right there. Now click on that.
On that?
Chapter, yep, chapter 2 practice. Click launch. Click begin.
It let me do that, but it won't let me do the lab.
All right, well now go back then. Go back the same way and go to one of the labs. So go to exercises lab exercises 1 and 2. Same way.
Lab
Lab
exercise.
exercises 1 and 2. Not that one. We don't have any. I don't know if, yeah, we do. You could use that one too. I'm sorry. Lab exercises 3 and 4. Go down. No, not this.
Oh,
Not
sorry.
this. Go down. Click on that again. Lab exercises 1 and 2. Now click on. Actually, no, I apologize. This is probably closed. Click on, and I'll open it up for you again, but click on, go to our class. Go to lab exercise, I'm sorry, we'll put it under that week. So click on that week that you're on right there. Now go down, scroll down. Okay, right there. Yeah, click on that. I'm sorry, click on lab exercise 3 and 4. Now click on cell division, examining mitosis. Click launch,
There we go.
click begin. Continue to lab simulation. You read through this and then you continue to lab simulation. See, now you're in it.
Okay, good.
Now,
I was getting it. It kept wanting me to put in a 2-week trial thing.
okay, well, you don't have to do it now, obviously.
Okay, I must have figured it out last night then.
If for some reason it brings that up later, that's when I want you to send me a lab shot. I'm using the wrong word, a screenshot showing that it's making you do that.
Why is this not going full screen for me?
Because if you click that, you see where that arrow that with the square, the double square
That one?
up on the very right top right corner, top right corner.
There we go. I found it.
Okay. That same thing is going to happen if you can't get into Wiley Plus. And you know what? Someone who can get into Wiley Plus, share their screen. Somebody who can get into Wiley Plus, share their screen.
I don't mean to cut anybody off, but I cannot get into that.
Which one? Which one?
The lab exercise 1 and 2B. I did the 1, but for the 2B, it won't. It keeps popping
Okay.
up Wiley Plus, and it says activation code or something like
Courtney, can you share your screen?
that. Yeah.
Let me stop sharing mine. Yeah, share your screen. Let me see what's going on.
Okay, so this is what pops up.
Okay. Now let's do something else. If you don't mind, go into your email for this class.
Okay. Well, this is my email for school. So
Okay, yep, and I should be on there. See that MC Gessel?
yeah.
Click on that one. Now go down, hello students, blah, blah, blah. log into my hack and navigate to course content to find the inclusive access link. Can you go into my hack?
Mm-hmm. This is my hack.
My hack. Now, there's something on there should say course content. So let's scroll through and just see if we see that first. All right, let's keep going down. Let's make sure it's really not there.
Yeah, I don't.
Well, let's just see if we're still not done scrolling. So I want to make sure it's really not there. Because what you see and what I see are two different things. Now scroll back one more time, scroll all the way to the top really fast.
Okay.
Let's make, let me just look just for a second. All right, go to bright space. Go to bright space on there. Go to our class, and it might be that lab exercises 1 and 2, B, A, and B are closed for right now, but I can open them up again. But let's go to lab exercise. Let's go to our class.
Sorry, my computer is a little slow.
It's all right. No, I understand that more than I can say. Click
Okay.
on, close that out if you can.
What, this out?
Your Norton. Is that you or that's me? Here, sorry,
Oh.
apologize. I don't want Norton. I don't need Norton. Go down to week 9/6/2021. Click on, actually, I'm sorry, let's wait. Scroll up here really quick. Go back to bright space. Let's make sure that it really isn't right here. Scroll.
Oh, just back to the regular?
No,
or
right
no?
here. Stay right here.
Okay.
No. Scroll down. Scroll. Scroll the resources really quick. Let's see what it says under that. I don't see it. Scroll all the way down here. Okay, click. No, scroll. I'm not scroll all the way down there. Scroll your screen all the way down.
Okay. Mommy's doing her schoolwork. Be quiet, please.
Okay, it's not there. So go scroll back
Yeah.
up again. Scroll back up. Now click content. Okay, go to week 9/6.
Yeah,
Now go down to the
go
lab.
ahead. I'm sorry. Go ahead. What did you say?
Go down to the lab. And click lab exercises 3, 3, and 4, and A.
Oh, this isn't
No,
the
this
right
is
one.
the PowerPoint. This is.
Yeah. I think it will let me get into it and do it. I was just wondering, because when I tried to do the.
Yeah, here it is. What does it say? You have to have, so you need that. All right. What I want, do me a favor right now. Can you take a screenshot? Scroll back up a little bit. Scroll back up. Scroll. Stop. Oh, go back.
Oh, you mean, okay, I see what you're talking about. Like,
Send me a screenshot of that, right? Well, wait, let me look really quick here. Course details. troubleshoot. Can you click on that course section details? See where it says course sec, yeah, right there. Does it allow you to click on that?
No.
Send me a screenshot of this right here.
Okay, so how do you want me to screenshot it? Just like
Hey,
send a, take a picture
I
and
don't
send
know.
it?
I honestly, I don't know how to take a screenshot. Does someone know how to take a screenshot? And can tell her how?
I mean, I can just take a picture and send it to you via email.
Send it to me.
There should-
If she has a Mac, it's Shift Command number 3.
No, it's
Command
not a
number
Mac.
3?
It's just a Windows.
All
There
right,
should be a print screen button up towards the top right of your keyboard. You could hit that and that should copy the screen for you.
I think I actually heard a picture taking.
Yeah, Professor, that was
Okay.
mine. Mine doesn't even load. It just gives me that spinny circle.
You have a pop-up blocker. I'm almost sure of it.
Was.
And what I need you to do is call Wiley Plus for that, because I can't, I think that's a pop-up blocker on your computer. And I have no idea how to disable them, but I know that's usually what happens when it's there. I'm not that big of a computer person, but I've learned from experience. I think that's a pop-up blocker, and you need to call Wiley Plus.
Yeah, I had the pop-up blocker too, but on my iPad, and I had like the Apple iPad. And I switched over to my HP laptop, and then I didn't have the blocker. I think it's an Apple thing. If you call them, or you can just disable the pop-up through like the settings that Apple has on their devices, but it's definitely an Apple problem.
Okay. So it is a pop-up blocker.
Yeah.
And if you have an Apple, Stacy's telling you how to deal with that. I don't know enough about computers, but I know that if you call them, they will tell you how to disable that on your computer.
Do you have the number for them? Because I went to their customer support and it was just like a web page about
Yep.
like,
Give me 1 second. I'll give it to you. 1 moment here. I'm sorry. Give me 1 moment here. Because I call these people all the time, and I know they're really good because I have them on my contacts list because I call them as frequently as I do. 1-877 725
okay,
7503.
this is Wiley.
Yes. So anytime you're either your McGraw-Hill or your McGraw-Hill or your Wiley Plus are not loading. You have access, but they're not loading. That's most likely a pop-up blocker. And I do not know how to disable those. But having had them more than a few times, that's what's occurring. You could also try calling the Hack IT Tech, but they might not be able to help you there. They're not going to be able to help you with the inclusive access and why you don't have access to it at all. But when it comes to why it's not loading, they can probably help you. They're pretty smart there. The Hack IT Tech, bear with me here because I actually called them yesterday. The Hack IT Tech is 1-717. Oh, you know what? Don't put the 1 in there. 717 780 2570. So if you, does someone want me to give them the McGraw-Hill? Let me give it to you just in case. It's 1-800-338-3987. So 1-800-338-3987. And most of these places, except for like Saturdays where they close around 8 at night, are open 24 hours a day. Because I've been asking them what their hours are when I call. And I know at least the Wiley Plus is open 24 hours, except for Saturday when they close at 8 p.m. And then they open again
So-
at midnight.
Sorry,
Go ahead.
the lab exercises 3 and 4A, so that's where we can find the Wiley Plus or whatever.
Yeah.
I have 3 days left. It says, should I
You have what?
put up 3 days left? And because I did like the free trial.
Right,
I missed the
when that Ashley, is this Ashley talking to me? Who's this talking to me?
Yeah, it's Ashley.
Ashley, when it ends, do it right now. When it ends, or do it when we have lab. Do it when we have lab. When it ends, try doing what I just was doing with Miranda.
Okay.
If it asks for that inclusive access code, like it did for Miranda right there, which you don't have,
Mhm.
send me a screenshot showing me that.
Okay, gotcha.
Because what I'm going to do is I'm just going to forward all these emails to the person over the biology books, because, you know, we're trying to follow their directions to how to get to it, and it's not getting us there.
Okay.
And I wish I could walk you through it really easily, but I don't get what you get on your screens.
Yeah, no, I agree.
All
Yeah.
right. You're welcome. Other questions, other issues? For the one person who said they're probably missing some assignments, do me a favor. Go back and send me a list of the ones that you're missing, and I'll extend them out for you. I'll extend out the deadlines for you. If you go into your grades, it will tell, I think it tells you what ones you're missing. You should, at this point, the ones that you should have done are the chapter 1 practices, the chapter 1 quiz. You should have open to you. You should have the chapter 2 smart book, you should also have the chapter 1 smart book done. Bear with me. Let me start again. You should have done at this point the smart book for chapter 1, the chapter 1 practice for chapter 1, the chapter 1 quiz, and lab exercises 1 and 2A and 1 and 2B, and the virtual lab simulation.
I have a quick question about the virtual lab. On D2L, it says that the due date is the 16th, but I got a 0 for the virtual lab, but it's only the 14th.
Is it the simulation or is it something else?
1 second. It just says virtual lab tutorial.
Okay, you know what, just go in and do it,
Okay.
because it's giving you a 0 until you do it.
Oh, okay.
Go in and do it.
Thank
You
you.
said it was lab exercises,
Yeah,
sorry, or 1 and 2A.
so you should have lab exercises, and they may be closed at this point, but I can reopen them.
Yeah, because mine's definitely not there.
The lab exercises 1 and 2A and 1 and 2B.
Okay. Yeah, I still have yet to do both of those. They weren't showing up.
Okay. Send me an email. If it says that it's closed to you or you can't access it, send me an email telling me which ones to reopen up and I can reopen them up. You need to tell me when you'll have them done by too.
Okay. I can have them done by today, but let me y'all send an email.
All right. Okay, let's get going on other stuff. If you have other things, let me know after class. I have about 20 minutes between this class and my next class, so we can figure some of this out. Let's see here. I may take part of our time in lab this week to cover some of our lecture material. Let's just see what happens though first. All right, let's see here. So remember when you're studying, and I don't have it posted here, but no, I don't have it posted here. It's on the previous week. Bear with me just for a second here. When you're studying, use this right here as a study guide for this chapter. For the chapter practices, you have an unlimited number of attempts. For the chapter quizzes and for your exams coming up at some point, you have 2 attempts each. No, I'm not doing this, people. Let me tell you, it's a little frustrating for me that you're getting that on Wiley Plus, and what they're asking you to do isn't there anyway. But we won't say anything. Because if you noticed, it said course content, and you don't. That is not an option you ever have. And then it says inclusive access link, which you don't have either. So I don't know, we'll figure it out. Okay. I think we were about, no, we weren't this far. I think we were right here. Approximately. Does this look about right?
Yeah.
Okay. So atoms, oh, let's get rid of this. Atoms are composed of some subatomic particles. We have protons, neutrons, and electrons. The protons are positively charged. The electrons are negatively charged, and the neutrons are neutral. typically when we draw an atom, bear with me. Typically when we draw an atom, let me back up. So the protons and the neutrons are in the nucleus, and the electrons orbit the nucleus. The protons are positive, electrons are negative. So the charges, the positive charge of the protons and the negative charge of the electrons keep the electrons orbiting around the nucleus because opposite charges attract. When we draw an atom, we typically draw an atom using the Bohr model method, this planetary method where the electrons are planets orbiting the nucleus, just like our planets orbit the sun. We draw it like this because first we have to be able to draw it. When we talk about reactions, and if you go into any future chemistry courses, you have to be able to draw reactions. And so we draw it in as a way that we can see where the electrons are. However, in reality, we know that at any given moment, the electrons are so small that there's no way to draw them. At any given moment, you cannot say exactly where one electron is. However, we have a general idea of the average path that they take. As they orbit the nucleus, we have a general idea as the average path that they take. So on average, it will be within this path, or it will be within this path. However, at any given moment, one electron could be up here, one electron could be right here, one electron could be down here. However, on average, this is where they're found. What that means is that with regards to an atom and the electrons around it, in reality, even though we draw it this way, in reality, it looks like this. Here's one orbit highly concentrated with electrons. Here's another orbit highly concentrated with electrons. So it's actually more like an electron cloud. In reality. So we draw it like this, knowing that it looks possibly more like this. But the only way to really visualize an atom is to be able to draw the electrons in there. So we draw it like this, knowing that it looks probably more like this. Electrons forming the electron cloud in an atom occupy regions of space called these electron shells. So this is one shell. This is another shell. Each of these shells contains one or more orbitals. Orbitals meaning one ring. The first shell contains one orbital. And each orbital has fills with 2 electrons. Each next shell contains 4 orbitals, and each orbital contains 2 electrons. So the first orbital contains 2, let me repeat this. The first shell contains one orbital that has 2 electrons. The second shell has 4 orbitals, with each orbital containing 2 electrons. So what that means is that the first shell can have 2 electrons. The second shell can have 8. Let me say it one more time. The first shell has 1 orbital, and that orbital contains 2 electrons. The second shell has 4 orbitals, and again with each orbital containing 2 electrons. And the third one has 4 orbitals, with each one containing 2 electrons. What that means is that the first shell is full with 2 electrons. The second shell is full with 8 electrons. The third shell is full with 8 electrons. And if we have one, the fourth shell is 8 electrons, and so forth. So 2, and then 8, until we're out of electrons for our atom. So moving forward, that wasn't what I meant to do. Moving forward. With regards to an atom, it is the smallest particle of any chemical element that still exhibits the chemical properties of that element. If you remember, we talked a lot about, in the first chapter, we talked a lot about structure and complementarity. You remember that? Structure and complementarity, or structure and function, and that that structure dictates function. And if we change the structure, the function's going to change too. This is the structure of an atom. If we change the structure of an atom by adding more protons or more neutrons or more electrons or taking away some electrons, we're going to change the function of that atom too. And if we change the function of an atom, which is the smallest particle of any given chemical element, we're going to change the chemical properties of that atom, making it into a different element, where it's going to display the properties of a different element. So, like backtracking just a little bit, this idea of looking at the Bohr models of atoms. Hydrogen has 1 proton and 1 electron. Carbon has 6 protons and 6 electrons. The first 2 electrons go in the first shell. The next 8, but in this case, we only have 6. So the next 4 go in the second shell. Case of nitrogen that has 7 electrons, the first 2 go in the first shell. The next 5, the remaining 5 go in the second shell. Oxygen has 8 electrons. So first 2 in the first shell. remaining 6 go in the second shell. Phosphorus, first 2 in the first shell, next 8 in the next shell, and the remaining 5 go in the third shell. Sulfur has 16. Two go in the first shell, 8 go in the second one, and 6 go in the third one. This number down below here, you see the 1 and the 6 and the 7. That's the atomic number, which the definition is on the next page. And it says how many protons that particular atom has. And in this case, it tells you how many protons are in each atom of sulfur. The number on top is the number of protons plus neutrons. In the case of hydrogen, hydrogen doesn't have it in the stable atom. So we'll talk about differences in a moment here. In the stable atom, there's only 1 proton, there's no neutron. In the case of carbon, there's 6 protons and 6 neutrons, which gives us an atomic number of 12. In the case of nitrogen, 7 protons, 7 neutrons gives us an atomic number of 14. And you'll see phosphorus is a little bit of an oddball here, in that we have 15 protons, but 16 neutrons. What that is that's what we call an isotope, which we'll talk about here in one moment. One more thing on this slide. The most outer shell here is the valence shell. In this case, the most outer shell is a valence shell. When we talk about chemical reactions, which is coming, it's the electrons in the valence shell that dictate which reactions are going to occur. Atoms are arranged on a periodic table. So the atoms of each element are arranged on a periodic table according to their different chemical properties. Are you expected to memorize a periodic table? No. I was a chemist as an undergrad. I can tell you that I don't have the periodic table memorized. Nobody memorizes the periodic table. However, you need to know how to use it. And you get better at that with time. I can tell you, I have a basic idea where many atom elements are because I've used it enough. But I do not have this whole thing memorized. If you gave me an exam and said, okay, fill it out, I couldn't do it. Moving forward.
I have a question.
Go.
Sorry, what all should we memorize?
You know what's on that. We'll talk more about that as we go. You don't need to memorize any of the periodic table, but you look at that chapter 2 worksheet. That's what you need to know for this chapter.
Okay.
And we'll talk, one of your questions asks you about how the elements are organized on the periodic table. That's this slide that we're looking at right here.
Okay, thank you.
You're welcome. So looking at this, this is how the elements are organized on the periodic table. Vertical columns are groups. So vertical columns are groups. Elements that belong to the same group, this hydrogen, lithium, neon, and potassium, all belong to the same group. These are elements that share the similar chemical characteristics, which means that they, for example, they all form the same type of chemical bonds. Horizontal rows are periods. If you look here, their atomic number 1, 12, 13, 14, 15, 16, 17, 18. If you go from left to right, their atomic numbers all go up by 1. Atoms of one period all have the same number of electron shells. So this one contains 3 shells, this one contains 3 shells, this one contains 3 shells, up until we get to argon over here. This one contains, hydrogen has 1 electron shell, helium has 1 electron shell. So when it comes to how it's organized, this is how it's organized, and this is the description down here. So for each atom, it has an atomic number, which is equal to the number of protons within the nucleus. In any given stable atom, so this is a neutrally charged stable atom, the number of protons equals the number of electrons. Do you remember what the charge is on a proton? Somebody go back and tell me what it is.
Would it be positive?
It's positive.
Oh.
What's the charge on a neutron?
Does it not have a charge?
It does. You're right. It doesn't have a charge. What is the charge on an electron?
Negative.
It's negative. So in a stable atom or a neutral atom, I think I'll have to put neutral there. In a neutral atom, the number of protons equals the number of electrons. So for example, this is a neutral stable atom here with a 0 charge on it, because the positive charge of the proton is neutralized by the negative charge on the electron. Also, the number of electrons within a given atom are going to determine the chemical behavior of that atom, which we'll talk about. We'll elaborate on that here in a moment.
So you're saying the positive and the negative cancel it out and equals a neutron.
Exactly. Exactly.
Okay.
It's not always the case. That's in a stable neutral atom.
Okay.
But when the number of protons equals the number of electrons, that means that the charge is 0. And that atom is stable.
Okay. But there was more of like the neutrons or something than
Yep, we're gonna talk about that here in a moment. but yes.
Gotcha.
The number of, so the mass number is the sum of the number of protons and neutrons. So for example, the one hydrogen atom has no neutrons. So its mass number is 1. However, atom comes in 2 other atomic structures. Deuterium is an isotope of hydrogen that has one neutron. Tritium is another isotope of hydrogen that has 2 neutrons. So isotopes are atoms with the same number of protons and electrons, but they have different numbers of neutrons. And the atomic weight is the average of all the relative weights, the mass number. The average, and I think I should change this to mass number. So the average of all the relative mass numbers of all the isotopes given for that atom. And so the mass weight is actually 1.08, 1.008, because neutrons have some mass. The most common form of hydrogen is this. However, we do see some of this and some of this in reality in the earth and in our bodies. Which means that the average atomic weight is this. You think atomic weight is the same thing as being the weight of the nucleus, the mass number meaning the weight of the nucleus. Now, question for you. The element lithium has 3 protons and 4 neutrons in its nucleus. What is its mass number?
It'd be 7.
Why is it 7?
Because don't you have to add the protons and neutrons to equal the mass number?
Good job, Isabel. Yes, that's correct. Good job. You're going to learn that a lot of times I'm going to turn around a question on you and say, well, why do you think that's the answer? Because sometimes you say it differently than I say it, and that helps everybody. And it also helps cement it in your head. Going back up, an atom with a mass number of 18 that contains 10 neutrons would have an atomic number of what?
8.
You're right, it has 8. And Catherine, do you go by Kate?
Cat.
Cat? All right, I'll
Yeah.
try to remember from here on out. It comes up as Catherine, but I was looking at your, I think I got an email from you or something, or it's in the roll and it says Kate, but I'll remember Cat.
Okay.
I'll try to remember Cat. Let's put it that way.
I don't mind.
Okay. So clicking right back to isotopes one more time. Same number, isotopes have the same number of protons. Isotopes of a given atom or element have the same number of protons, same number of electrons, but different numbers of neutrons. And if you think about it, in this particular slide, they're comparing apples to the different isotopes. So a crab apple is one type of atom of hydrogen. Golden Delicious is another type of atom or isotope of hydrogen. And a Granny Smith is another different atom of hydrogen. Radioisotopes are heavier isotopes of many elements that are very stable, very unstable, and their atoms decompose spontaneously into more stable atoms. These are what we call radioisotopes. So heavier isotopes of many elements are unstable, and their atoms are going to decompose into more stable atoms. This process of decay or atomic decay that results in many explosions is called radioactivity. This decay involves an emission of alpha, beta, or gamma rays from the atomic nucleus. If a given isotope, a radioisotope, if it gives off an alpha ray, it's going to give off 2 protons and 2 nuclei. Another different type of radioisotope can give off a beta ray, which is 1 electron. Another isotope can give off a photon or a gamma ray. So every time this parent isotope gives off something, it becomes this and gives off this. In the case of this an isotope that gives off a beta ray, it becomes this and gives off this. Actually, let me put this a different way. Every time a parent isotope decays, it gives one that gives off alpha rays is going to give off a helium nucleus and become the daughter isotope that's slightly different. You can see that it's slightly different from that. Anytime that a radioisotope gives off a beta ray, it gives off an electron and becomes this. Anytime that a radioisotope gives off a gamma ray, it gives off a photon and becomes this. So these elements over time may transform into other elements. If we keep taking away a proton and a nucleus, or 2 protons and 2 nuclei, see, 2 protons and 2 neutrons, eventually we're going to become something else. Our nucleus is going to change so much that we become something else. Same thing with electrons. If you think about this for a moment, remember how an atom with the same number of protons and the same number of electrons has a 0 charge. If this atom gives up this particular atom that has a 0 charge, gives off an electron, its protons and electrons no longer equal. And it's going to have a positive charge because its protons equal, number of protons equal, exceeds that of the electrons. So these elements, or these radioisotopes of these elements, can transform into other elements. All radioactivity can damage tissue. Alpha emission is the least penetrating, meaning the least damaging also. Inhaled alpha particles from, however, inhaled alpha particles from radon cause lung cancer, second only to smoking, that results in cancer. So they are somewhat damaging. They can damage and result in cancer. Gamma emission has the greatest penetrating power, the most damaging power, and the most penetrating, meaning able to invade tissues. This is used to destroy localized cancers for that reason. Ionizing radiation. Remember, these are beta rays, so beta rays are the ones that give off the electrons. Knock electrons, here's our radioisotope right here. They knock electrons out of atoms. And these electrons then go on to damage other atoms. When we start forcing electrons out of atoms that then are unstable and try to join up with another atom, they start changing the structures of the atoms they join up with, which is eventually going to result in chaos. You keep changing the structure of things, you change their function. So you change the structure of one atom, you change its function. It then goes on and changes the structure of another atom because its electron goes off and it causes damage to another atom. And you keep changing the structure of all these atoms, which changes their function. And they're no longer, as a result, they're no longer going to be doing what they're supposed to be doing. That's why ionizing radiation is so damaging. Any questions?
No.
Okay. Radioisotopes gradually lose their radioactive behavior. So they gradually become a more stable atom. As they continue to decay, they gradually will become a more stable atom. The time required for any radioisotope to lose half of its radioactivity to become a more stable atom is its physical half-life. To lose half of its activity. If you think, some of you I know work in medical healthcare fields. If you think about a medicine's half-life in the body, is how long does that medicine remain in the body? How long is it until half of that medicine is no longer in the body? It's been excreted or it's been neutralized or something. Same thing here. The amount of time required for one radioisotope to lose half of its radioactivity is its physical half-life. These half-lives can vary between hours to thousands of years. For example, the half-life of cobalt-60 is 5.27 years. Right here, but for it to go from 10 grams to 5 grams is 5.27 years. The biological half-life of a radioisotope is how long does it take for it to lose half of its radioactivity within the body. I would guess that, no, I won't even guess that, never mind. So biological half-life is how long it takes for a radioisotope to lose half of its radioactivity within the body. How long is it before that atom, that radioisotope is no longer giving off half of its radioactivity? Mom, if you want to put her in here, you can. So we often use radioisotopes. If you remember, almost the first day or the second day, we talked about PET scans, positron electron emission scans, tomography scans, positron emission tomography scans. In that case, we're using a radioisotope. We radioactively label a given isotope and watch its metabolism within the body, watch its breakdown in the body. So they radioactively label glucose, inject it into a vein and watch its breakdown in given structures of the body. The more it breaks down, the more radioactive decay or emission it gives off. And then we measure that amount of radioactivity that it's giving off. So we can use this to study the function of different molecules within the body. This, for example, this is a regular thyroid using radioactively labeled iodine. However, in Graves' disease, that shows symptoms of hyperthyroidism, so increased activity of the thyroid, this is how much emission is given off instead in the same experiment, with the same amount of radioactively labeled iodine being introduced. For any particular element, the number of blank can vary. Therefore, the mass number of an element will also vary. What's the answer? What would cause the mass number to vary? First off, define the mass number.
That's the sum of the protons and neutrons.
Right. So does the number of protons vary very often?
No,
No. So what's probably varying?
the neutrons.
Right. So the answer is D. Molecules and compounds. A molecule is two or more atoms held together by chemical bonds. And a compound is two or more atoms of different elements bound together. So every compound is a molecule. But not every molecule is a compound. Because compounds are two or more different elements. Well, what if in the case of oxygen, the elements are the same? It's just a molecule. So two or more atoms held together. Each molecule can be represented by a molecular formula that identifies the number of atoms of each element in a given molecule. So in the case of water, down here, this is its chemical structure. Paisley, don't lick me. Stop. This is its molecular formula. Stop, don't lick me. Sorry, I got a dog on my lap. Don't lick me. Methane. This is its chemical structure. Excuse me, this is its chemical structure. This is its molecular formula. A molecule is the smallest particle of a compound that still exhibits the same characteristics of that compound. So a molecule is the smallest particle of a compound that still exhibits the same characteristics of that compound. So the molecule of salt or sodium chloride, which is right here, is NaCl. However, when you normally see sodium chloride or salt or sea salt, it looks like this. It's in more of a block form. But the smallest molecule of sodium chloride that maintains the characteristics of that compound is this. The molecular weight is the sum of the atomic weights of the number of atoms of each atom within the molecule. So for sodium chloride, we have one sodium and one chloride, giving them it a molecular weight of 58.44, 58.5 grams. Any questions? Don't lick me. Stop licking me. Molecules with the same molecular formula, but in which the atoms are structurally arranged differently, are what we call isomers. For example, ethanol, which is what's found in alcoholic beverages, has a structural formula of, has a condensed formula of this, structural formula of this, has a condensed structural formula of this, ethyl ether has a structural formula of this, showing how the carbons are attached to the oxygen, how the hydrogens are attached to the carbons. You can see that it's different. The lines here are showing how the different atoms are constructed and to which other atom they're bound to. This is ethyl ether. This is what they use. I think they used to use to put people under before they realized that it was a carcinogen. This is what you find in alcoholic beverages. This is a gas. The condensed structural formula of ethyl ether is this. For both of these, they have very different chemical properties. One of them is a liquid, one of them is a gas. However, their molecular formula is the same. So the chemical and physiological effects of two different isomers or properties can be very different. Isomers. An example of isomers, L amino acids. So the L and the D, you see the D up here, the L and the D are two different configurations of a given amino acid, which is the individual subunits that are incorporated into proteins. So each of amino acid can exist as an L shape configuration or can exist as a D configuration. However, only L configuration amino acids are incorporated into proteins. So their structure, even though they have the same, these would have the same molecular formulas, their structural arrangement is different. So only L amino acids are going to be incorporated into proteins. These cannot be incorporated into proteins. Any questions? So chemical bonds and the role of electrons. So if you remember, one of the things that was in one of the previous slides was that the number of electrons in the valence shell is what's going to determine the chemical properties of any given atom. What that means is the number of the electrons in the chemical shell, in the valence shell, are going to determine the reactions that that particular atom will participate in. With that in mind, when atoms of a given chemical element combine with other atoms, they are held together by chemical bonds. This is an energy relationship between the electrons of the chemical atoms. So this is an energy relationship between the electrons of the reacting atoms. The likelihood that an atom will form a chemical bond depends on the number of electrons in the valence shell. Now, do you remember how many electrons are in the first shell?
Is it 2?
It's 2. Good job. And Ashley, good job. How many are in the second shell? Ashley?
Could be 8, right?
It's 8. How many are in the third shell?
8.
How many are in the
Okay.
fourth shell?
8. It gives 8
Okay.
on. It gives on.
It just keeps going, yes. So when the valence shell contains 8, that atom is most stable and it will not react with other things. This is what we call the octet rule. If you think about an octagon with 8 sides, the octet rule says that the atom is most stable when its valence shell is full with 8 electrons. So an atom will react with other atoms in order to get 8 electrons in its valence shell. Sometimes it gives up electrons. Sometimes it takes on electrons. And other times it will share electrons. That's the basis of why atoms react. Let's take 10 minutes and come back to this. So let's come back at 11:02 and come back to this. See my other teaching assistant. Yes, see my other little teaching assistant. Very morally supportive. Yes. She doesn't know what to do when she's bouncing around on her feet. But you notice that when she's outside, it's all over the ball. Yes, then you have to watch her. Yeah, we won't say that you got out in front of the stuff. It's like, seriously? And I thought, don't even look at it. Oh, she moves up though. Yeah, I'm here actually. Yeah, I know. I'm cute, and that's supposed to be awesome, but I really don't. she doesn't, she wouldn't understand the science. That's what helped her. Because she's never had a fear about it. Yeah, I don't know. Well, maybe. Just a little talk. Just a little. Just a little. Sure, that helps us to see if it's just a little fast. Right? Probably not. Oh, yes, yeah. Mhm. Oh, yeah. So, next to those, we'll see it. No, behind us. If I'm behind, because we spent so much time trying to get into that mountain. I'm even looking at that thing on the screen. It says follow these directions. We're doing it. Nothing that they asked for is there. So I'll call that guy again for the books after class. So, got to fix this. Yeah, and I don't know how to, I mean, if it's not there, you know, you can tell them to follow these directions, but if it's not there, it's not there. They say click on course content, it's not there. Click on the inclusive access, it's not there. And I know it's not his fault. Right. I think it's a publisher. Yes. But he's the only one that I know how to contact. And that's why he's the old guy. Solve this problem now. Well, I may help this work out with that one. I won't. I'm the one who made the choice to do this with my students. They didn't realize it was going to be this big of a lot. You know, I've never had it be this difficult to get the students into a class. Get access to their books. Which makes me really wonder why Lee and Morocco. But now it's maybe why it's really why. And they keep sending me this. They send me instructions, and so I'm looking at the email with my student, following the instructions, trying to follow the instructions. But what they say to look for and click on is not there.
Okay, so I sent you the email just saying, I guess just saying I don't have the access to the lab 1 and 2.
Yes, and I probably won't be able to call them right after class, but I'm gonna
Okay.
call them I'm gonna call them this afternoon.
Okay.
And I think what I do is I call the person who's in charge of the bookstore and getting these books and working with the publisher to make this work. And let
Okay.
them know that what they're asking us to do is not something we can see on the screen. Like we never
Okay.
saw that inclusive access link.
Yeah, I know. So like, you said don't take, you said screenshot it, or should I not?
Send
are
me
you
the
just gonna call them?
screenshot. Send me the screenshot, and I'm gonna forward it to this guy, but I'm gonna email him first. And then I don't know
Okay.
if you heard any of my conversation I just had with my mother / roommate. I said I'm gonna threaten to never have students buy this book again with this inclusive
Yeah,
access.
because too
If
much
it's-
trouble. Yeah.
Well, if it's this big of a pain in the neck, it doesn't.
Yeah, then why
need
would you want
to
to
be
go
this-
through it
Yeah, it doesn't need to be this difficult.
again? It
And
should be.
And yeah, and I don't understand why it's being so difficult for some of you when you've all paid your tuition. And then
Yeah.
not being difficult for other students.
Okay,
So-
so to get there, go to lab exercises 1 and 2, and then screenshot,
Yeah.
or 1 and
Well,
2.
not 1 and 2, 3 and 4. 1 and 2 is close to you, but I will reopen it.
And 3 and 4 is under the week of 9/6, right?
Yes, and
Is
it's
that
in the sub-module for labs.
Okay, I'm looking. Oh, lab exercises 3 and 4. Here we go.
Yeah, you should.
Three-
You could even go to lab exercise 5, but I'm guessing it's going to say the same thing for you. It's not going to
Okay, so I
say
click on-
anything different.
Click on the lab exercises 3 and 4A.
If you go to the
That's what-
Ashley, if you go to the second, if you go to
Okay.
week 913, you'll see
Mhm.
lab exercise 5,
And go to that one.
but I think it's going to say the same thing for you. It's not going to be any different.
Let's see. I know
Does
I have the extended trial for 3 more days.
Well, keep doing that.
That's-
Keep doing
Should
that.
I?
But I will send. I'm
No,
gonna
now
get.
it's saying now
What?
it's saying 2 days left. It's saying 2 days left now,
Right.
but still.
Well, we'll work this out. We're gonna work
Okay.
this out. But I think I'm gonna get a little ornery this time around when I contact them, because I'm
It's like-
really kind of tired of this process. It shouldn't, this is something very basic to your success in the class, and they need to get it figured out. And I can't figure it out for them. That's why they have to figure it out. But so be patient with me, but yes, send me that and I will forward it and I will say, look, this is what's going on. Why don't they have access?
Okay.
But
No, I appreciate it.
it's my job. It's my job because I'm the one who said, let them pay for their books with their tuition. And so when
Right.
you paid your tuition, you got access to the books. That was the way it was supposed to work. You shouldn't be having to try to pay access to it now. Because
Yeah, that's not-
you've already paid for it.
Right. We came out of the tuition.
Yeah.
Um,
So let's go forward here.
Okay.
So each electron shell within an atom represents a different electron level. If you remember, we talked about the fact that the electrons are negatively charged, the protons are positively charged. And the electrons orbit the nucleus and stay next to the nucleus because of the opposite charges. Opposite charges attract. However, we can move an electron out to another orbit by having it absorb a certain amount of energy and pull it away even further. If you've ever played with magnets, they pull together, the opposite ends go together, and then you pull them out, you pull them out, you pull them out. and at a certain energy, and it takes a certain amount of force to pull them out. You have to keep working on it, keep pulling them out. What that means is that the electrons, bear with me. There has to be a certain amount of energy that holds the electron, any electron, this electron right here, a certain amount of energy that holds it away from the nucleus. And because if you have a negatively charged electron and a positively charged nucleus, and the electron is rotating around the nucleus, what's preventing the electron from colliding into the nucleus if it's attracted to the nucleus? Nothing. So there's an energy that's preventing the electron from moving into the nucleus. If you want to pull the electron even farther away from the nucleus, you have to add another amount of little bit of energy. Because with those two magnets, you got to pull it a little further away. If that electron that absorbed a certain amount of energy moves out here, it can also give up that same amount of energy and bounce back down to the orbit it was at before, or the shell it was at before. However, once that electron gets further and further out, if you, having played with magnets, everyone's done it at some point probably. It gets out this far, you got to hold them away from one another to keep them from going together. Then a little bit more energy, a little bit more of a pull it out a little further. And then beyond a certain amount of distance between the nucleus right here and the electron, you don't have to put that pull on it anymore. There isn't the attractive force anymore. So what that means is that the electrons that are closer to the nucleus are held closer to the nucleus. The force on them to keep them close to the nucleus is stronger. You have to take on a certain amount of energy to get further away from the nucleus. Certain amount of energy to get further from the nucleus. But as this keeps going out, eventually that force that's attracting them to the nucleus is going to drop off. So electrons, the inner electrons within closest to the nucleus, are not going to take part in reactions with other atoms because they're held more tightly by the atom's nucleus. The electrons farthest from the nucleus in the valence shell are going to have the highest potential energy because they're being held the furthest away. And they're most likely to interact chemically with other atoms. So the valence shell electrons follow the octet rule. Remember, we like to have 8 electrons in this valence shell. And if you look, this is an oxygen atom. It's got 2 electrons in the inner shell. It's got 6 in its outer shell. How many does it want? How many does a valence shell want if it follows the octet rule, which it does? Somebody tell me.
Aiming for 8.
It wants 8, so it's either gonna take or it's gonna share 2 more electrons. It's either gonna take 2 more electrons or it's gonna share them. And in the case of water, which is H2O, so 1 oxygen atom and 2 hydrogen atoms, it gets those 2 electrons by sharing them with hydrogen. Any questions? So atoms, to get that 8 electrons, bear with me, can either gain electrons to get that 8 in its valence shell or lose them. Atoms like oxygen that have 6 in their valence shell are more likely to gain 2. Atoms that have 2 in their valence shell and need 8, or need to get 6 more to get 8, are going to give up those 2. This is whatever's thermodynamically easier. Is it easier to if I'm an atom and I have 2 electrons in my valence shell and I need 8 in my most outer shell to be stable, it's easier for me to give those 2 up and go with my shell right underneath that original valence shell that's already full. I just need my outer shell to have 8. I need it to be full. So it can be easier for me to give up 2 rather than take on 6. Or, for example, what if I have 7 in my valence shell? It's easier to gain 1 than it is to give up 7. I just need 8 in my most outer shell. Whether I give up 2 and have 1 less shell, 1 less electron shell around my nucleus, that's fine. I just have to be able to have a stable outer shell that's full. So an anion is an atom with an overall negative charge, because this atom gains electrons. If you remember, what's an atom that has a neutral charge, the number of protons equals the number of electrons. Let's say that my outer shell, I'm a neutral atom. My outer shell has 6 electrons. It's easier for me to gain 2 than to give up 6. So I gain 2 electrons. At that point, when I gain 2 electrons that are negatively charged, I still have once I gain those electrons, my number of electrons is going to exceed that of the number of protons that I have by 2. So the overall charge on my atom is going to be a -2. A cation is a positively charged atom. So this is a neutral atom that, for example, has 1 electron in its valence shell. 1 electron in its valence shell. It's easier for it to lose that 1 than gain 7. So that's the case of sodium right down here. It's easier for it to lose the 1 than gain 7. So it loses that 1 electron. So now the number of protons in this atom exceeds the number of electrons by 1. And because protons are positively charged, this atom now has a positive charge of 1. This is a cation. In the case of chloride or chlorine that took on the electron from sodium, the number of electrons now exceeds the number of protons by 1. So this atom now has an overall negative charge of 1. And ions with opposite charges are attracted to each other. Reactive properties or chemical behavior of an atom mostly depend on the number of what?
I would say D.
Why do you say it's D, Genesis? Why do you say it's D?
Because the outer shell kind of is the reason why stuff like connects in certain ways. I don't know how to put it into words.
You know what? I think that was perfect. Let's say in the way it binds with other stuff, but that was perfect. What is the scientific term for that outer shell? Do you remember?
The valence shell.
Good job. Yeah, that was perfect. When atoms gain electrons, the atoms become electrically neutral. Sorry, let me have you answer this. When atoms gain electrons, what's the correct answer? Someone besides Genesis.
The atoms become a negatively charged.
You are right. Now, let me ask you this, Ashley, on the same question.
Mhm.
What if they gain 2 electrons?
It would be a charge of it's like -2 or something like that.
Good job, -2. What if they lose electrons? And let's say that they lose 3 electrons.
Okay. Would it be +1?
No, let's say
Or
they
positive?
lose 3 electrons.
And they had 2, right?
Well, we won't even worry about how many they had
Okay.
before. If an atom has 5 electrons and they lose 3, They lose 3.
Would it be positive?
Positive 3.
Yeah, I'm gonna say positive
Why?
3.
Why? Can you tell me why?
You said they're losing 3, right?
And so now the number of protons that they had is now 5. The number of protons that they're going to have now is 5. And the number of electrons they have is 2. So the overall charge is going to be a positive 3.
Yeah.
Now let me give you one more example. One more.
Okay.
This atom, for some odd reason, gains, I have an atom that has a positive charge of 3.
Mhm.
It gains 2 neutrons. What's its charge now?
Positive charge of 3, and it gains 2 neutrons. It'll still be positive.
As it
Am I
still,
right?
what is it? What is it? Is it become positive 1 or 2, or is it still positive 3?
Because it's neutral, wouldn't stay 3.
Yeah.
Or would it be
What's the charge on a neutron?
It's 0. There's no charge, right?
Right.
So it would just be it'd just be the same thing. It'd be 3.
Good
Stay as
job.
3.
Good job. That's exactly right. What does it become at that point? What is it now? It's not, what if the number of protons now doesn't equal, in this case, number of protons is not going to equal the number of neutrons. What is it at that point? What is it called?
Would it be the catron or the anion or whatever it's called?
What about
Like
an what about an isotope?
Okay, it's an isotope. I missed that one. I'm glad you're like testing me though. Helping me.
No, I understand. And I'm more than I can say.
Yeah, it helps. This is a lot of information, but yeah, I think I remember back in high school as well.
Okay, well,
I-
you're doing great. So let's just keep moving forward. Are there other questions? Anyone else? I don't see any faces today. So are any other questions? No. Inorganic compound salts. So ionic compounds, remember these are, when we refer to ionic compounds, we're talking about cations other than hydrogen ions and anions other than hydroxide. So these are cations and anions that are held together because of their opposite charges. When dissolved in water, the ions dissociate. When they dissolve in water, so they get pulled apart and the water kind of separates them. So the sodium and the chloride are together, then you add water and water separates them away from one another by neutralizing the charge on the ions by the water and the hydrogens interacting with it. In this case, ions are called electrolytes because they can conduct an electrical current in a solution. The most common salts found in the body are sodium chloride, calcium carbonate, and potassium chloride. If you see, I'm going to start using just chemical symbols. And the reason is because I want you to go to a periodic table and start learning some of these symbols. You can also look these up in Google and say, what's this supposed to be? And if you put in NaCl, it'll tell you it's sodium chloride. If you put in calcium CO3, This doesn't even need to be lowercase. It's going to come up calcium carbonate. Other common ions are iron with a +2 charge, iron with a +3 charge, copper with a +2 charge, zinc with a +1 charge, iodine with a +1 charge, and magnesium with a +2 charge. So any case where the number of electrons is, or the number of protons is greater than the number of electrons by 2, it's going to have a +2 charge. When the number of protons is greater than the number of electrons by 3, it's going to have a +3 charge. Case of copper here, +2. So the number of protons is greater than the number of electrons by 2. In the case of zinc, the number of electrons is less than the number of protons by 1. Just reversing what I was saying up here. For iodine, the number, in this case, the number of electrons is less than the number of protons by 1, and therefore it has a +1 charge. In the case of magnesium, this has a +2 charge, meaning that the number of protons is greater than the number of electrons by 2. When, with regards to this electrolytes up here, when salts dissolve in water to release ions, the fewer the ions, the lower the electrical conductivity. So the lower its ability to conduct a current. The more ions, the greater the electrical conductivity. Electrolytes are substances that ionize in water. And therefore form solutions that are capable of conducting electrical currents. We can detect electrical activity in muscles, the heart, and the brain with electrodes on the skin, because electrolytes in the body fluids conduct currents from these organs to the skin surface. Often the way that seizures are detected, seizure activity. It's how we do an ECG, which you'll learn a lot about next semester. What? EEG for the brain. No, but I'm talking about an ECG for the heart. But it's an EEG for the brain. What does it stand for, Mom? What EEG, what does it stand for? Electroencephalogram. Okay, so in the case, she just taught me a new word. When with this, so this is an electrocardiogram when they're looking at the heart. This is an electroencephalogram when you're looking at the brain, because encephaly, if you remember cephaly meaning brain, encephaly is brain. So this is an EEG or an electroencephalogram. This right here, this is a lie detector. So an electrolyte balance is one of the most important considerations in patient care. Imbalances can lead to coma or cardiac arrest. Most major electrolytes and the ions that are released when they dissolve and dissociate in water: calcium chloride, disodium phosphate, magnesium chloride, potassium chloride, sodium bicarbonate, and sodium chloride. One thing, we talked a little bit about radioactivity, something that's similar to a radioisotope that gives off the ionizing radiation are unstable, highly reactive chemical particles with an odd number of electrons. Remember how atoms like to have 8, like to have 2. We can generate, in the body, we generate what are called free radicals. We generate them all the time in just normal metabolic activities. They can also be generated by radiation or chemicals. So oxygen, in the case of cellular respiration, is converted to what's called a superoxide anion. This by itself is very dangerous, because if you remember that gamma, that beta ionizing stuff, when it breaks down, one of the electrons, this electron in this case, goes off and attacks changes another atom, and when it changes that atom, it changes its function. So if we keep changing the function of atoms by adding electrons to them when they're not supposed to have them, that's going to cause chaos. Because if we change the structure, we change the function. And for our bodies to work a certain way, they have to have the same functions. So free radicals are short-lived because they combine with other biomolecules by giving up the odd electron, converting other biomolecules into free radicals that then go on to destroy other things. Oxidative stress is a state that occurs when there's too many free radicals in the body cells. When we've got too many things with an odd number of electrons that go on and react with other things. When they react with other things, they change their function, causing chaos. Oxidative stress can cause cells to lose their structure and their function, thus leading to diseases like cancer, diabetes, aging, atherosclerosis, and at least 45 others. Many of our diseases, we believe, this little dog that I have sitting on my lap here, who's my favorite teaching assistant because she just is morally supportive as she falls asleep during my lectures. she's developing cataracts. If I remember right, and I need to Google it, but cataracts are a sign of oxidative stress. Antioxidants inactivate free radicals. By doctors, and we're constantly being told to ingest more antioxidants. Antioxidants neutralize free radicals by giving up electrons to free radicals, and therefore giving, rather than having the free radical have 7 electrons in its outer shell, that'd be an odd one that has 7, it gives up an electron to make it so it's not reactive, because now it has a full valence shell. So it donates an electron to free radicals, neutralizing the free radical. So anytime that we have unpaired electrons, that's a highly reactive substance. If we pair that electron with something else, it makes it a lot less reactive. It either makes it a lot less reactive or it makes it unreactive, depending on what it is. So these are the common antioxidants that we were often encouraged to ingest in order to neutralize the free radicals that are constantly being formed in our body. Superoxide dismutase, or SOD, is an enzyme that breaks down potentially harmful oxygen molecules. So this breaks down superoxide. This one that has an unpaired electron. It's a regular enzyme in our body that it defends against oxidative stress by breaking down superoxide. Breaks it down into hydrogen peroxide, which is the same as hydrogen peroxide found in a bottle that you can buy in a store, and breaks it down into water via a catalase. And of course, water is neutral and unharmful. Isn't harmful, let's say it that way. Ionic bonds. These are the bonds that are formed between an anion and a cation. So these bonds are formed by the transfer of one or more electrons from one atom to another, which results in the formation of ions that are then attracted to each other via their opposite charges and create a salt. Common ionic bonds are commonly formed when an atom has 1 or 2 valence electrons, or atoms with 6 or 7 valence electrons. So this is remember, atoms that have 1 or 2 valence electrons only, and they need 8 to be stable, are more likely to give up that 1 or 2. And they're more likely, they give them up to atoms with 6 or 7. which allows one atom allows both atoms to have full outer shells. In the dry solid state, ionic compounds are salts, which do not exist as individual molecules, but they exist as crystals that are large arrays of cations and anions. However, not all atoms give up or donate completely their electrons. Most atoms do not. Most atoms share electrons to have a full valence shell. So rather than giving up an atom completely or taking on another atom completely, they share with another atom. So these are the most common and the strongest chemical bonds. These bonds are formed by electrons being shared. And the shared electrons occupy a single orbital. Remember that there's 4 orbitals within a shell. So these electrons, each one of these, this bond right here, this is one shell, this is one shell. They share 2 electrons between the 2 oxygen molecules here. Actually share 4. Sorry, they share 4. 2 here, 1, 2 being shared with this oxygen atom, and this oxygen atom are sharing this electron, this electron, this electron, and this electron. And these are kind of smashed together because of the slide. But this atom and this atom. Water, this atom and this atom. Any questions? Single covalent bonds is where one pair of electrons are being shared, like in the case of a hydrogen gas molecule. One pair of electrons is being shared, so 2 electrons are shared, which equals 1 pair. Types of chemical bonds. Or double covalent bonds. 2 pairs of electrons are being shared, like in the oxygen molecule. So 4 electrons are being shared and 2 pairs with 2 pairs. So each pair has 2 electrons. So there's 2 bonds because there's 2 pairs of electrons being shared. In the triple covalent bond, 3 pairs of electrons are being shared. In an oxygen molecule, how many electrons in total? So oxygen with two oxygens bound to one another. how many electrons in total are being shared between the two atoms?
I want to say 2.
Okay,
But I'm not sure.
it's actually it's 4.
Is it 4? Oh yeah, okay. Because of the diagram you showed.
Okay.
Oh.
So because it's, let me backtrack just a little bit. So right here,
Mm.
yeah,
Yes. Yep.
we have covalent bond is when they're being shared. A non-polar covalent bond is when the electrons spend equal times around each of the nucleus of the atoms that are sharing those electrons. Equal time sharing. So things are being shared equally. So this is a non-polar covalent bond. Nevertheless, not all atoms share electrons equally. So polar covalent bonds are when the electrons are not being shared equally. One atom, one nucleus of an atom, attracts the shared electrons more strongly than the nucleus of the other atom. So even though hydrogen needs an electron, chlorine is holding on to that electron more than hydrogen is. Whatever electrons hydrogen has, chlorine is holding on to them stronger. This is a polar covalent bond, where this chlorine atom is attracting the electrons from hydrogen more than hydrogen is attracting its own electrons, or the shared electrons. If it helps you, the way that I think of this is I think about what do you know about the 2 poles of the Earth? We know that there's 2 poles on the Earth. We have one and I'm by no means a geologist or a world understand geography very well. But we have a South Pole and a North Pole, right? These are 2 extremes, right? They're 2 extremes. When we refer to a polar, we're talking about 2 extremes. And with regards to charge in this case. So just to compare up, a non-polar covalent bond shares electrons equally between the 2 atoms. There's no net charges on either of the atoms because they share them equally. Number of protons around this one equals the number of electrons. Number of protons on this one equals the number of electrons. Things are shared equally. There's no separation in charge. They're both neutral. However, in a polar covalent bond, the bonding electrons are unequal because the chlorine holds on to the electrons a lot more than the hydrogen does. So the result is that chlorine has a partial negative charge. because it has the electrons more often around it. And therefore the number of protons is less than the number of electrons on average. In the case of hydrogen here, because its one electron is more often around chlorine, its proton is left exposed, meaning that this has a partial positive charge. And in the case of the ionic bond, the net transfer is of one or more valence electrons, with full charges resulting on the two ions. So this isn't a sharing, this is a giving up or taking. Any questions? So small atoms, think small atoms meaning the number of protons. Small atoms with usually 6 to 7 valence electrons are electron hungry. They attract the electrons very strongly, like chlorine over here, like fluorine right here, like oxygen right here. These atoms are what we call are very electronegative. These are the ones that are more likely to pull the electrons off something that isn't and hold on to them a lot more when sharing than other atoms. Most atoms with 1 or 2 valence shell electrons have a very low electron attracting ability, like hydrogen here, and are described as being electropositive. They tend to lose their valence electrons to more negative elements, electronegative elements. So the electronegativity of an element depends on an atom's atomic number, because that will define the size of the atom. Remember, the atomic number is the number of protons. The distance of the valence electrons from the atom's nucleus. The further the further the electrons are away from the nucleus, the easier they are to pull off the atom. Remember when we have the two magnets, the closer the negative charge is to the positive charge of the proton, there's a certain force there that we have to, that's there. And we have to maintain that force to keep the electrons from colliding into the nucleus. However, the further we get out away from the nucleus, that force that's holding them together diminishes. And the easier it is, the further it gets out, the easier it is to pull that electron off of an atom, any given electron off. The further that the electron is away from the nucleus, the easier it is to pull it off. This is what's called the ionization energy, which is the energy required to move the most loosely bound electron from that. Electrons that have a high electron ionization energy, meaning it's a lot harder to remove the electrons, are the more electronegative elements. The closer the valence electrons are to the atom's nucleus, the stronger the pull of the nucleus has on the electrons. So the harder it is to remove them. Any questions? I'm sure you have questions, or you're wrapping your head around this. Any questions?
So this is recorded, so like it's going to be posted to the
I will
class web.
post it. I have to post it. I won't have time to post it today.
Yeah.
Let me see if I can't post it tomorrow.
Okay.
Water, in a water molecule, the oxygen is the electronegative atom. And so it attracts hydrogen electrons more strongly because of its higher electronegativity. This results in a partial negative charge on the oxygen because it pulls the electrons more its direction. And results in a partial positive charge on the water. So the whole overall molecule is polar, with a positive end on this end and a negative end on this end. So these are oxygen, because of the electronegativity of water that's much greater than that of hydrogen. The result is that we produce a polar covalent bonds, where the hydrogen has both of the hydrogens have a partial positive charge and the electrons have a partial negative charge. With regards to, oh, wait. So let me just summarize here. Molecular polarity. Non-polar molecules have covalent bonds where the electrons are equally shared, meaning that the electronegativity within them is balanced. The amount of pull that are on the two electrons being shared, or the pair of electrons being shared, are equal. Polar molecules involve bonds where the electrons are not being equally shared. One of the atoms is much more electronegative than the other that it's bound to, meaning it pulls the electrons more its direction, leaving the other atom exposed. So looking at this periodic table up here, what is these little arrows say? Increased electronegativity across, going from left to right and from bottom to top, meaning the most electronegative is right here. Least electronegative is approximately right here. But hydrogen is more not electronegative. So anytime that hydrogen is bound to a molecule along right here, bound to an atom belonging to these elements, and it's not equally balanced, the result is that you're going to have an electronegative atom, like hydrogen bound to chlorine, oxygen bound to hydrogen, methanol, which is what's in wood alcohol. Don't drink it, it causes blindness. Is very electronegative because of the oxygen atom. It's right here. It's bound to a carbon and hydrogen. Methane, an oxygen gas. Oxygen gas is not polar because both oxygen, if it's paired like this and bound like this, they're equal in their electronegativity, the two atoms, because they're the same atom, meaning it's nonpolar. So a partial separation of charge or two poles, a dipole, is created. In this case, the chlorines are bound to a carbon, which is less electronegative. So the chlorines on all four of these bonds is pulling on the electrons from the carbon more than carbon is pulling on. They're more electronegative than carbon is. And so they're pulling on the electrons from carbon more towards them, resulting in a partial positive charge of the carbon and more electronegative charges, more negative charges on the chlorines. Same thing with water here. Also, because a partial positive charge will be more attracted to a partial negative charge on another atom. So the result is that polar molecules, just like your little magnets, polar molecules, just like a dipolar magnet, which most magnets are dipolar, they only like to bind one way, and they only attract one way. Polar molecules orient themselves towards other dipoles and toward charged particles. Only a partial negative charge attracted to the partial positive charge of another molecule. Sodium here, sodium ion has a positive charge on it, which means that when you dissolve a sodium ion like sodium chloride, you put sodium chloride into water, the water molecules orient themselves so that their partial negative charges are all directed specifically at the positive charge of sodium, and the partial positive charges are directed out. So polar molecules, because of this ability to orient themselves, play essential roles in chemical reactions in body cells. one of the first things that polar molecules do is they very easily form hydrogen bonds. So we talked about ionic bonds, where it's a give or take of electrons completely. Talked about covalent bonds where they're shared. Hydrogen bonds are where hydrogen that's linked to an electronegative atom to create a polar molecule, where the partial positive charge on that hydrogen is then attracted to a partial negative charge on another polar molecule. So the partial positive charge of a hydrogen is attracted to the partial negative charge on another polar molecule, forming a bridge. Hydrogen bonds are important in intermolecular bonds, which bind different parts of a large molecule into a 3D space. These functions of hydrogen bonds serve as links between molecules and help determine the three-dimensional shape of large molecules such as the DNA double helix, proteins, and hormones. Oxygen is electronegative and hydrogen is electropositive. This means that what? Means what? Let's go back. This means what? This means what?
Would it be B?
B is in Bravo or D is in Delta?
E as in Bravo.
Okay, they're not shared equally.
Okay.
They're not shared equally. If something is more electronegative and hydrogen is more electropositive, meaning it's more likely to give them up.
So would it? Okay. Hold on a second.
Say it again. Clinton?
I'm just thinking of the answer. So
Okay.
would it? I don't know.
If oxygen is more electronegative, it means that it holds on to the electrons more than it allows. So in a bond between oxygen and hydrogen, oxygen is going to hold on to the electrons more, making it more negative. Hydrogen is more, as a result, has to become more positive. So the answer is C. The oxygen pulls electrons away from the hydrogen and becomes more negative, because the partial charge on oxygen is going to be more negative. I've got 2 minutes here. One more type of chemical bond. So we know that polar molecules have a partial positive and a partial negative charge. And you remember how we talked in the very beginning about how electrons, being able to document a given location of any electron is not possible. At any given time, you cannot determine exactly where an electron is because of that electron cloud. So electrons around an atom show random fluctuations in where they are, which means that just like a polar molecule that can have a partial positive and a partial negative charge, an atom at any given time can have one side that's more positive and one side that's more negative. And the result is that these slightly positive opposite charges attract. These are what we call van der Waals forces. They're very weak. These forces are important to protein folding, binding of proteins to each other, and interactions of lipid molecules within cell membranes, which we will talk about a lot in lab this week. This is a summary of the bonds that we've been talking about. I'm not going to read it. You can read it. I know you can, so I'm not going to read it. Any questions? I know class is over. Are there any questions?
So the second week lab exercises are due tomorrow, correct?
Yes.
Okay.
And go ahead. Say it again.
Which labs are those?
3 and 4.
3 and 4, they're due tomorrow. Okay, thank you.
Yes. And as soon as I'm done here, I think I'm going to call that the guy at the school with regards to the textbook before my next class. Other questions?
I have a question.
Go.
Okay, you're saying we're looking at our grades to see if we're caught up on everything. What is this on the first of my list? It says nervous system, and I don't have any points for that.
Bear with me. I'm going to stop recording just for a second.